I did want to do another video about transformations, just to show you that other cool things can happen. They don't have to be so simple as scalar multiples or just shifts or stretches. One of the easier ones to understand is the absolute value transformation. If you have a function f of x that looks like, say you got something that's looking like it could be, say, this. What would it look like if you went to graph absolute f of x? So if you saw the last video, you know that there are interior transformations and exterior transformations. The exterior ones work on the f of x values, and that's what this one is. This is an exterior transformation. It's a pretty simple one. F of x is established first, so all the y values are there, and then what you do is you take the absolute value of those y values and you replot those. So when you take the absolute value of a number, what happens? Well, if the number is already positive, nothing is going to happen, which is to say that for values where f of x is already positive, which is here and here, nothing is going to change. Right? These are all called fixed points under the transformation. It means that when you apply the transformation, those points don't get changed. If you're looking for more difficult transformations, what you're going to want to look for first will be fixed points. What points don't get changed? So everything that's positive will stay exactly as it is. Absolute value switches negatives to positives. So what's going to happen is it's going to preserve these, and this part here, it's going to flip up. Only that part is going to flip up. So you get something like this in the end. And that's an absolute value transformation. So if you see something like, if I were to ask you to say, give me a rough sketch of y equals absolute, say, x squared minus 2. All you would have to do, if you can draw up a sketch of the inside, then you should be good to go. So this, what I have circled, is the parabola shifted down 2 units, so that's going to be like this. And then when you apply the absolute value transformation to that, what's going to happen is this part's going to stay the same, and this part's going to get flipped up. So this is how it goes. Not too bad. This is one of the easier ones. But so it's going to delete this and preserve this, and that's the first one that I had in mind. The second one I had, what else can we do to these functions? You could do, if I graph, let's say, I'll make it simple. I want to do this. Alright, so that'll be my f of x. What's it going to look like if I apply the square root transformation? So, again, is it interior or is it exterior? It's exterior, because f of x has already been established. So what's it going to do? It's just going to take the square root of all the y values that you have. What's it going to look like? I go to my pen here. So, well, first you're going to ask yourself, what are the fixed points? So what points don't get changed? What numbers, what y values are going to stay the same after you take the square root? So anything that's 1 is going to stay the same because the square root of 1 is 1. Similarly for 0, the square root of 0 is 0. So these are going to be our fixed points. So what's going to happen with all the other values in between? Well, we just have to take the square root of those values. So when you take, so these y values in here, they're all between 0 and 1. And when you take the square root of a number between 0 and 1, it actually gets larger. So how it's going to transform, it's going to kind of introduce itself into a little curve here, and it'll look something like that. Alright, so just like that. For the y values in here, since you can't take the square root of a negative, there's just not going to be any part of the graph here. Alright, it's just going to get thrown away because it's negative. You can't take the square root of a negative, so it's out. The same thing is going to happen over here. The numbers between 0 and 1, they actually get larger, like that. And then we'll go around here to pick another nice point. This y value is 4, the square root of 4 is 2. So what's going to happen between here and here is these numbers are greater than 1, and the square roots of numbers greater than 1 are less than. Numbers get smaller when you take their square root. So it's going to look like, if it's going to be nice and smooth, it's going to look something like this. And just come up and down like that. And that's what happens when you take the square root. Alright, so no big deal. If you do a couple dozen of these, you'll find it becomes pretty routine after a while. But there are still a couple hard ones. What else do I have here? This one's pretty easy, but it might be cool to see. We have the squaring transformation. Again, it's exterior. So you just, all that you got to do, right, f of x is x squared, all that you got to do is take the y values and square them all. Let's go for the fixed points first. So any number that's going to be 0 or 1 is going to stay the same under the transformation. So what points are going to be fixed? This point's not going to move, and this point's not going to move, and this point's not going to move. This, and all these. These are the ones that are going to stay the same. Now we can kind of draw our function around these points using these as kind of a guideline here. What else can we do? We can take the values that are easy to square. Say this y value is 2, 2 squared is 4, so this point is going to get sent here. And the negatives, when we square those are going to kind of flip up too. So negative 1 squared, this is going to get mapped here. And this one, negative 1, is going to get mapped here. And this 2, or this negative 2, is going to get mapped up to here. Right? Negative 2 squared is 4. And so what's it going to look like in between again? Well, we'll take, maybe I should use red. When you square numbers between 0 and 1, they actually get smaller. So the curve that it's going to form is going to be underneath the actual line. It's going to go up like that. And as the values increase linearly, this is just going to be, this is just like a little, since this is just a straight line, this portion here is just going to look like a regular parabola x squared up to there. So you square all these and they get bigger. This one's a little steeper, so the curve has to be a little bit more pronounced, like that. And this is going to come to a point here. No, actually, I don't think it's going to come to a point. I think it is going to be a smooth transition. And then this is going to be like this. And then this one is going to come up like that, squaring all the outputs. And then the last part, this is going to go underneath. And then just flat line, stay flat. These are all fixed. So that's the squaring transformation. Another one, this one, something different. I want to send f of x to 1 over f of x. I want to do the reciprocal transformation. Some weird things that are going to happen on this one, because what you have to do is take all the y values and reciprocate them all. So what's that going to look like? Well, what will the fixed points be? What points stay the same when you flip them? Those are only 1 and minus 1, so 1's going to stay the same, and minus 1's going to stay the same. So these points are going to stay fixed. Alright, the y values. And then what are some other nice ones that we can flip? Whenever the y value is 2, you flip that, this is going to get sent to 1/2. And same thing down here, we have a minus 2 here. When we flip that, that's going to go to minus 1/2. And let's see, what else? And we got, let's see, 1, 2, this 2 will go to 1/2. And this 3 will go to 1/3. Alright, that actually gives us not too bad of a guideline. Now what's going to happen when we get near 0, this is where it kind of gets funky. Alright, we're taking all these y values and we're flipping them. So when the y values get smaller and smaller and smaller, when you flip them, the values are going to get larger and larger and larger. So as this line gets closer to 0, the reciprocal values are going to blow up. And what's going to happen is it's going to produce an asymptote. Wherever we get zeros, we're going to have, wherever f of x has a 0, its reciprocal is going to have an asymptote. So let me just draw that in. Alright. Make it a little bit easier. So over here we're going to have 1, 2. Alright. Sketch that in. And that'll give us an even better idea of how to continue with this. So alright, now what's going to happen from this end? Well, it's still going to 0, so it's going to approach the asymptote again, but it's negative. So what's going to happen? It's going to come up from negative infinity and do something like this. Go through the fixed points. Right? Comes up like that. And then it's just going to go back down to the other one. Like so. And then from the other side, since we're positive again, we're coming from the positive end. This is going to come way back down. And since the function is blowing up, its reciprocal is going to get smaller and smaller. So it's going to be like this. And that's the reciprocal function. Alright, that's what happens. So it's going to be, it actually gets kind of nasty. It doesn't resemble the original whatsoever. But that's what happens when you flip things around. So what else do we have? Let's see. Oh, okay. We have a different kind of composition I have in mind. If this is the graph of f of x, what would the graph of f of x look like? What's going on here? So, let's see, is it interior or is it exterior? I would say that it's an exterior transformation, because you establish f from the get-go, and then on those outputs you rework f. Now watch how this goes. It looks like it might be a little bit confusing, but it's actually not that. It's not so bad once you get a couple of them going. I would suggest starting with individual points here. Let's start back here. We'll start with -3 and tell me where it goes. So minus 3, f maps -3 onto 1. So -3 goes to 1. And then what do? According to this, you operate f again. Okay, you have to operate it twice. So I say -3 goes to 1, and then f of 1 is 4. So it's like a two-step process, alright? You do it once, get like the interim value, and then you do it again and plot that final answer. So I'll do that in red. So -1 ultimately got mapped onto 4. Now I have no idea what this thing is going to look like. I'm just going to make a bunch of straight line segments, and I'm just going to plot it at the integers and just connect whatever it is that I wind up getting. Alright, let's try this again. Alright, let's start at -2. -2 goes to 1. And as we know, 1 goes to 4. So this point here is going to get sent here again. Alright, try it again. -1. Let's see. I'll say -1 goes to 2. That's a change. Where does 2 go? So -1 goes to 2. 2 goes to 2. So that's going to be a fixed point. This point is going to stay, right? Operate f twice. It sends it. So -1 goes to 2. 2 gets sent on to 2 again. Let's go with 0. I'm kind of tired of making this list here, so I'll just kind of wing it here. 0 gets sent on to 3. 3 gets sent to 0 again. So that's going to come back here. So 0 goes to 3. 3 goes to 0. It's a safe bet that up until then, up until here, the function is going to look like this. It's going to be straight line segments here. Try out 1. 1 goes to 4. 4 goes to -1. So 1 ultimately gets mapped onto -1. connect that. How about 2 again? 2 goes to 2. And then 2 goes to 2. So that's ultimately going to, so here, that might be a little bit confusing. Let me do it again. I'm plugging in the x value of 2. So 2 gets sent onto 2. And then when we rework f on that, 2 gets sent back to 2 again. So ultimately 2 gets mapped here. The same thing. So that's a fixed point. Right there, that's another fixed point. We'll finish this off. 3 goes to 0, so 3 goes to 0, and 0 goes to 3 again. So this goes up here, and we connect those. How about 4? 4 goes to -1, and -1 goes to 2. So 4 ultimately goes to 2, like this. And at last, 5 goes to -1, and we already said that -1 goes to 2 again. That's going to be here. And we have composed f with itself, and that's what the graph looks like. I really didn't know what that was going to turn out to be. They just wind up, there's really not a whole lot of rhyme or reason to it. But it can be done, and that's how it goes. So that was, I think all of those were exterior. Yeah, they were all exterior. Now I want to do an interior. Let's say f of x goes to f of absolute x. Interior transformation. Alright, we're modifying the x values first. So this is a little bit more tricky because we have to deal with the input first. But let's see, what is it going to do? What will our fixed points be? Well, we know that if x is greater than 0, alright, whenever x is over here, absolute x, so like in this region here, absolute x equals x. And nothing is going to change. All of these points are going to be fixed, right? Because the absolute value bars don't have any meaning for x value, for inputs that are already positive. So these all stay. But what's going to happen over here? Well, when we go over to these values, the sign of the input is going to get reversed first because the absolute value bars come first. Let's see how this goes. If I make, let's say x equals -1. The first thing I'm going to do is hit it with absolute value and turn that into +1. And then I'm going to work f on it. So I put in -1, I hit it with absolute, and I get +1. And then I do f. F of that is going to be 4. So -1 gets mapped onto 4. And try this again, see where this is going. -2. Hit it with absolute. It turns into +2. And then you work f on it. So -2 goes to +2. F of +2 is 2. So that's going to go here. Alright. Keep on going with this. -3, say. Hit it with absolute, you get +3. And then f of +3 is 3. So what's going on here? You'll notice that the same thing is going to be true for all the interim points here. If I plug in these numbers here, the absolute value is going to put them, it's going to flip them around and make them over here, and then operate f. So the net result is this part of the graph, anything where x is negative, is just going to get thrown away and replaced with the mirror image of whatever's on this side. See that? And that should make sense because, right, f can only operate on these positive values. It deletes all of these, turns them into these, and then f operates and it's just going to mirror it. So that was a little bit more complicated, but it can be done. Interior transformation, throws that away, mirrors that over here. Next to last one I have is, we'll say, alright, let's say that this is f of x, and we'll start off with an exterior. I want to go from f of x to greatest integer of f of x. Now, if you remember what the greatest integer does, basically what it does is it rounds down. The outputs are going to be the integers. So The final result of this graph is only going to lie along these lines. There's going to be nothing in between because you can't get non-integers out of the greatest integer function. Once again, what will our, but it's an exterior, so how bad can it possibly be? What will our fixed points be? That's a good question. Let's see. It should make sense that wherever f of x is going to be an integer, whenever the f has an integer output, those are going to be our fixed points because the greatest integer the fixed points of the greatest integer of x are the integers themselves. If you put integers in, you're going to get those same numbers out. So wherever f of x is an integer, like say 1, right? The output is 1, and the greatest integer of 1 is 1, so this point is going to stay fixed. Same thing here. The output of f is 2, so the greatest integer of 2 is 2. Similarly for here, and here, and all these. So the points that wind up on the integers themselves, they all stay fixed. So then the question becomes, what happens with the interim values? Look very carefully at what's going on. Remember, it's exterior, it can't be that tough. Look at these values here. If we operate the greatest integer function on these values inside here, notice they're all between 0 and 1. So what's going to happen to them, they're all going to, got to change color, they're all going to round down to 0, right? Numbers like 1/2, 2/3, 1/4, they all get rounded down. So what's going to happen is these are all going to become like a flat line here, up to but not including here. Right, these all get rounded down. At the very last second, this one jumps up. Right, because at this point it reaches 1, so it's going to go through a change. Now, all these values in here, in fact, these ones and these ones, they're all between 1 and 2. So they're all going to round down to 1, with the exception of this one point here. Right, this is where it is. This one's not going to change. So what's going to happen is it's going to look like this. All get rounded down like that. Right, round down, 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 except for this one, which is a 2, that stays. Everything else goes down. And once you get the hang of this, you can see where it's going to go. These interim values are going to round down to 0. These interim values, all these ones, they all get rounded down to -1. So it's actually a part of the graph there. See that? And then finally these ones here, they get like this. So fill this in, and the red is the greatest integer acted on a function f of x. Just to round it down, looks pretty weird, but makes sense, that's what it is. The last one I have in mind is a tough one. That's going to be, we're going to send the function f of x to f of the greatest integer of x. So we're going to do the greatest integer first and then operate f. And this could be a little bit tricky. But once again, we'll talk about what will our fixed points be. Let's see. If I make x equal to 1, 1's going to round down to 1, and then f of 1 is going to be what is going to be this number here. So that point is going to stay fixed. All right. These vertical lines are going to be the integers, right? -2, -1, 0, 1, 2. What if I put in 0? The greatest integer of 0 is going to be 0. And f of 0 is going to be this. So this point is going to be fixed. What about 2? I plug in 2. The greatest integer of 2 is 2, and f of 2 is this. So this point is going to be fixed. It appears that it's going to fix all the points like so. Right? I put in -1. Greatest integer of -1 is -1. F of -1 is still this. So then what's going to happen to the interim points now? Well, think about it. We're operating the greatest integer first. So what we have to look at is sets of numbers sets of inputs between the integers. So all these numbers in here, Alright, let's take these ones for example. Between 0 and 1. All numbers between 0 and 1 round down to 0. And then f operates. So numbers like 1/2, they round down to 0, and then f comes in. So we'll take 1/2, round it down to 0, f of 0 is this number here. What about 3/4? 3/4 rounds down to 0, then f of that is going to be, then f of 0 is going to be this. You see, they all agree with whatever this number was here. So what's going to happen is everything is going to be just like this up until that point, whereupon it's going to jump up again. Alright? And then we look at these numbers inside here. Numbers inputs between 1 and 2. They all round down to 1 first. And then f operates. So if x is between 1 and 2, they're all going to round down to 1. And then f is going to operate. So it's going to take on the same set of values that it did when x was 1 exactly. So that's going to be like this. And if we had more of this function coming out like this, say, alright, and say the number over here, all of these numbers between 2 and 3, they round down to 2 first, and then f operates. So it would look like this over here. So then just coming at it the other way, if x is between -1 and 0, they all round down to -1, and then f operates like this. And then numbers between -2 and -1, they round down to -2, and then f operates. So I wonder if that's going to be, yeah, I think that's clear enough. They're all going to be like this. So it looks a little bit like the other one. Alright, it's got the same kind of characteristics, only the value is going to be the same for every, the output of this one is going to be the same for every value between the integers, and that's a consequence of the fact that you're rounding down first. Now, this is about as hard as they get, I think, and if you can follow this, then I think that you can pretty much handle any transformation that comes down the pike.